I'm going to follow up my last video on propositional logic with something called conjunctive normal form. Or CNF. What this is a way to reduce things like propositional logic, a logical formalism, and other things like first order logic, other logical formalisms, into the same representation. So we'll have, we can call it like a logical system. We're going to turn it into CNF, and then we're going to solve it with a SAT solver. So the problem is called 3-SAT. SAT stands for Satisfiability. This is the canonical NP complete problem. So essentially all these logical things and a bunch of other NP problems, we can boil them all down to 3-SAT. So it's this sort of mother of all problems. The 3 in it, sometimes it's just called SAT for satisfiability. There's this little interesting side note of 3 is sort of this truly magic number. So we're going to end up expressing everything as something like this, where we have up to 3 variables all disjuncted together, or with ORs, so X or Y or Z. And maybe something like this, or Z or W. So each of this would be a whole thing would be a clause. And all the clauses are combined together with ands. So that's hence the conjunction. And what's interesting is however you boil it down into a CNF formula, you can always reduce it down to 3 variables in a clause. And this is NP complete. Now, sometimes in special cases, you can get down to 2. If there's 2 variables, it's called 2-SAT, and that's actually in polynomial time. So there's a lot of problems, this is total side note, that when you go from 2 to 3, become basically intractable. So 3 is this sort of magic number. Tesla is right. It's sort of this weird special number out there. But anyways, that's sort of a side thing. The main thing is I'm gonna show you something called CNF. Whoa, okay, went crazy with the highlighter. That we can reduce all logical systems down to basically all of them. There might be some sort of side notes on this, but all the major ones can be reduced down to this, and then we can solve it. This is just an example, again, that I was using last time of propositional logic, just to give you an example of what a logical system might look like. We have variables, and then we have these rules. And we set the variables to either true and false. So that means player 1 played rock, set the true. If player, whoops, got a little excited there. If player 2 played paper, we set that equals to true. Then we look for an assignment for the rest of these variables. So we set, where's player 2, paper, there we go. We try to set an assignment for the rest of the variables and to satisfy all the rules. And from there, once we have an assignment, then we can ask a bunch of questions like, oh, since player 1 played rock, player 2 played paper, we can then infer player 2 won. So yeah, nothing earth-shattering in this example, but we can see that by coming up with an assignment for all the variables in question, we can answer all these more interesting questions. So that's what satisfiability is at a high level. Again, this really boils down to, again, for all the variables in the system, we need to find an assignment of true and false to each one that satisfy the sentences, that is, the rules. So to be satisfied, if the premise is true, the conclusion must be true. If the premise is false, this could be true or false. The conclusion could be true or false. So these are both the satisfying cases. However, if the premise is true but the conclusion is false, that means our rule doesn't hold. So it's, let's say, not satisfiable. So that's the sort of meta rules, the constraints we're working within to develop. So this is what the name of the game is. So we're working within these rules to determine, can we satisfy this system or not. So this is just an example. So it's a lot more trimmed down than the rock paper scissors example. So often we have these variables, we have rules connecting them all together, and then typically a few will be set to true or false. That's sort of like our knowledge base, or our starting facts, if you will. So I'm going to put a little T here. So that means, and I'm just going to follow just basically my intuition. I'll get to the algorithm of how to do this later, of which there are actually a few. I'll show you the most general one. But we know for this rule to be satisfied, since we want this to be true over here, we'll set this here. So I'm just going to sort of also guess a little bit. So I'm going to set x to false, which will make this true. This premise true and this premise true. So this to be satisfied, we'll set this to be true, right? Because if y was false, then that rule would not be satisfied. I'll set x to be true. So that means z to be true, it has to be set to false, right? Because we're going to toggle it here with the negation. So if we set z to be false, then we're fine. Let's just go through and check the rest. So we have false or not y, so that's also going to be false. So again, so this rule is, as soon as the premise is negated, so as soon as it's false, it doesn't matter what's on the right hand side. Now we have false and, I almost wrote out and, I don't need to write out and, false and true. So again, this is fine. It doesn't matter what's over here. So all these are satisfied. So let's say, yay, it's satisfied. Now let's work with the same system but with different starting facts. So we're going to fix y and z to be false. Okay, so if this is false, so this rule's conclusion is false. This one's conclusion is true. All right. So this is, the danger zone over here. So we need the premise to be false. So to do that, we have to set x to be true. So that way this is false, this is false, because we can't have this rule up here be violated. So now, since x is true, we have not y. So actually both these are true. So it's true or true. So it's super true. That means we have to put a true value in for w to make this rule be satisfied. Now, if we have not y, so that's going to be true, and w is true, z we've already set to be false as a given. So that means this rule, we're not satisfied. So this is an example of not satisfied. So even the set of variables and rules, there could be some settings where it works, some where it doesn't, where it's satisfied, not satisfied. If it doesn't matter which settings you have of the variables, what assignments you have, then you're basically in the world of a tautology. But so we see that it's not a given that you're always going to be able to find a satisfying assignment. So there's an inherent contradiction in here. There's no way to with those facts to make it work. Now, conjunctive normal form. So we're thinking about, well, so let me get down to what is conjunctive normal form. We want, again, variables. We can have our Boolean variables, but we only want to use and, or, and not. So the biggest one is, can we do away with the premise, or really it's this conclusion or conditional operator. So we need a way of reducing this down to just these sorts of symbols. So that gets us actually pretty close to like almost Boolean algebra. So the answer is, can we do it? Yes. So if we think about the implication or conditional statement, where we have x being the premise and y being the conclusion, you can actually express it as this, where you have not x, the premise, or y. And if you just walk through this table, you'll see the why that is. So we can see, if they're both true by our original satisfying, so we'll have it work out so that true will be equal to satisfied. So when it's satisfied here, we're going to say, yes, this works out to be true. This is the case that it's not satisfied, right? So if the true premise and false conclusion, so that's false. So if we have not x, so we have false or false, so that's also going to match false. Now, last two cases, again, if the premise is false, it doesn't matter what the conclusion is. So that's why we mark these as true. And in both of these, since we have x, not x, and both these x is false, these will both be marked as true. So you can see this statement is logically equivalent. So that means we can basically just do away with this operator. Let's see how we're going to do that. So if I take this rule from before, my earlier example, that's where I'm starting. I'm going to replace the conditional with that, if I go A, arrow B, remember we can do not A or B. So that's what's happening here. I'm just negating the premise and ORed with the conclusion. This is De Morgan's law here. So I'm distributing in the not, which flips, if you pay attention, it flips the disjunction, the or, to an and, or a conjunction. So now the only other thing we're going to do is, again, we for CNF, we want to have this setup where we have 3 or fewer disjoined, so altogether ors, and something else. V would be a terrible variable name if you're wondering. It's the worst A ever done. So we want it in this form, and this is kind of awkward that we have this sort of parentheses, this grouping here, which is centered around an and. We want it to be sort of centered around an or. You can just basically distribute the or. So you end up with X or W and Y or W. So now we're in full CNF. So then I'm just going to show you this example here. So this would be the conclusion of that system. So I'm taking, I'm negating the premise. That's how I could just get, so I go from, not X to X, and then replacing this with an or. So that's pretty straightforward. Same thing here. So then there's a couple steps in here, right? So that's my previous example, where it takes a few steps to get there, plus De Morgan's law. This last one, Since I'm negating y and w with z, again I'm going to apply it to Morgan's law. So I have y. Oops. Oh, this is actually a little typo here. Look at that. Or not w or z. So this is a fine CNF triple. Now all these are, to make the system complete, we're going to put essentially a parentheses around each of these and do and keep one that write a. I throw an and in here. Oh, don't write an a. Oh my goodness, it's too late. And there we go. So you can think we can make this whole thing a series of, the first one and the second one, and we get 2 from the next one and the last one, right? So then we have this huge Boolean expression. So this whole thing ends up being this huge Boolean expression. Now, let me actually just finish here. So now we have this huge Boolean expression, right? We don't have any implications or conditionals or whatever you want to call them. We just have this huge formula. So this is also sometimes called a formula. Yeah. And we can, it's pretty clear if you assign x or y to a particular value. Again, this should work from before. Send x or y to, like if you could work through it. If I set x is equal to false, y is equal to true, z is equal to false, and w is equal to true, you'd find that this whole formula would be satisfied. So if you did all the logical workings of it, actually, let me just write that out. This will take a second, but let's just go for it to be super clear. So I have x or y and x or not z and not x, w and y or w, and it's a little bit unfortunate. I was hoping to get it all in one line. And you might be wondering, if you're really sort of eagle-eyed or quick on your feet, well, why couldn't this go over 3 variables in a clause? So again, each one of these, just say again, each one of these is a clause, hence the clausal normal form. You could always introduce new variables to sort of expand out the number of clauses you have. And by doing so, you can always boil it down to 3, but you can't do 2. But that's a little bit of a tangent. But yeah, so if I have x being false or true, so that means this whole thing's going to be true, so I'm going to highlight that yellow. We have false or true because z is false and we're negating it, so this is true. Now we have x is false, we flip that to true or true. Okay, this is satisfied. And now we have y is true and w is true. Okay, this one's satisfied. So we have, just quickly recapping first one's true and true and true and true. So essentially we just need every clause to evaluate the true, and we're good. So then we have true here, false, and z is false. But because we have one true in there, the whole thing's good. So our whole system then boils down to this big string of clauses all ANDed together, and we have to make sure each one evaluates the true. So it just means one variable needs to be in the right configuration for the clause to work. So that's the conversion. That's me working through that example. There was the very first slide of my example with this, where I found the satisfying assignment. So that means let's start thinking about, as I kind of jumped ahead, let's think about search. So if I just have one clause here, I didn't want to write the whole thing out, but I can think, well, now for each, let's say this is my only, these are my only two clauses in my whole formula to satisfy. Now I could think for each variable, so there's x, y, and w. Each one can be true and false, true and false, true and false. So we have this sort of 2 to the n, where n is the number of variables, expansion here. So it's not great, but we can see if we can take this formula and we can just say, oh, let's assign x to be true. So now we end up here. So where we've replaced x with a particular value. This one's where x is false. This one's where y is true. See that it's plugged in where y is false. And then when w is true. So we have 2 spots to plug that into, and 2 spots there. So we can see this is actually great. So now we can start to think of this as, each, basically it's a search tree, right? So we can now frame this whole logical problem. We went from rules to this formula. Now we have this formula, and we can think about all the assignments we can do. Now we can work through this like it's some big tree of, I have something, my whole formula here. I have a ton of assignments that gives me new partially satisfied potential assignments. And then maybe some of these just don't work. Some of these look really promising. So this means over here, once I set w to be true, say in this example, it actually doesn't matter what the other ones are. So this is a really good branch, where some of these are looking more problematic. So setting w to be false, there's only one configuration there. But so this allows us to basically do, DFS, that's a terrible D, DFS in the space of CNF, DFS in C and F. Yeah, I hate acronyms, but you get the idea. So this is pretty neat. We have, again, if you remember my n-queens problem, my n-queens, again, this would correspond to, this is I want to highlight, not cross it out. This would correspond to, we put a queen in a place where there's a conflict. There's no point to finish the rest of the board. We can also get down to these where if I, again, down here, decided set y equals false and some child on this one, it wouldn't matter what x is, right? So then we have false or false. This clause is done. So then, so this child over here would just be pruned off, or we set y equals false down here. So we can see we have the same thing. So we don't have to do it exhaustive, but we do have to do a lot. And the amount we have to explore is really based upon sort of the structure of these formula. So it's really hard to say exactly how long it's going to work, but it's really not great. So yeah, and we'll have like n layers here. So it's going to be in this to the n category for SAT. And this is just me pointing this out for, a little bit more. So if I had this formula, this would be a complete assignment. So I have something done for each one where I have assignment for, X, Y, and W. This is complete and satisfied. This would be like a dead end. So if I had set W to false, and for some reason set Y equals false, we don't need to bother looking at. Oh, my tablet skills are lacking. We don't need to bother considering what to do with X. We're just done with this. So this is sort of a dead end node in our search tree. So this is the backtracking procedure. So this looks very close to that. If you remember my pseudocode from N Queens, I'm just going to be given this CNF formula here. I'll clarify that a little bit. Say, well, there's no solution. The stack's not empty. We'll get the current one. We'll check if it's valid. So if valid, that's like the dead end. So if it's not a dead end, continue. If it's complete and satisfied, remember that as a solution, then we'll end up just quitting. If not, we're going to look through each variable and value that's unassigned in our current formula. We'll assign that variable to that value in the current, so let's modify it and then put it in there. And that's it. So that's how we can backtrack through it. So there you go. DFS, ends up saving the day, solving everything. But wait, there's more. Can we do improvements? Yes, we can. So if there's two things, they're considered heuristics. That's a fun word. Or shortcuts, you can think. One's a pure symbol, the idea of a pure symbol. So if a variable has the same, so you can call it like polarity, maybe is the right term for it, where either all of them have nots or negated, or none of them do. So like W is pure. Actually, everything in this is pure. So if it's pure, that means we don't need to consider the world where W is false. There's no point to that. We can just scan our formula and say, W has to be true. Or there's no reason. It's only the impure symbols that are a problem for us. So if it's pure, like W here, good old nice boy W, very pure, you just set it to true. There's nothing to consider. There's no reason to backtrack or branch or any of that stuff. Another one is the unit clause. So once we start to fill in things and we get these sort of loners, sad W is by himself in this clause, well, once we get down to this, or let's say, actually a better example, literally scratches out. Let's say for some reason this is false. Again, it's basically a no-brainer that W should be true. So once we're down to this scenario, it's true there, but should be false. Where there's only one, we only got one. There's only one possible way to solve this particular clause, and we have to satisfy them all. So then we know W has to be true here because we have false or, well, it has to be true. So that's what we call a unit clause. So these are both shortcuts. These are places where we know we're never going to have to backtrack. We just make the assignment. So that cuts it down even further. So now we have basically a tree where we come out here, and then some of these are just a straight shot down to the next. Where this old dummy over here has to branch out a lot. This one, hey, because we got purity, we're going straight ahead. So that's what that does for us. These are these no-brainers with weird names that we can just fill in. So if you add that in, so this looks, you could think, oh, this looks almost exactly the same. It's true. So this be consistent. I add this single function call here. So the rest of the framework is the same. This just goes through the assignment current formulation and just does that. You think it's just a for loop. You scan it. You look for anything that's pure unit. Make the assignment. Then you need to scan again because once you assign some unit things and some pure things that might change the status, you might have to do it again. So you could think you just do that multiple times so you can't fill in anything else, and then you come out here to backtrack. And this is, I always forget the name of this. It's Davis, Putnam. Where are my notes? Davis, Putnam, Lodgeman, and Loveland, or DPLL. So this is a somewhat famous algorithm. It's basically DFS with these shortcuts that's in there. So it's DFS plus this little juiced up, just a little bit of logical roids, if you will, to sort of shortcut the places where we don't really need to search. But you can extend this, this is a great SAT solver. It can solve, all sorts of things. I accidentally implemented this for fun once. I didn't even know what I was doing, but I was working on Sudoku. So you can solve Sudoku. There we go. I implemented this because you can basically use your rules, of like the rows, columns, and diagonals and blocks and all that kind of stuff. And for placing things, but then occasionally if you have to guess, that's where you jump in the DFS land. So yeah, this just makes us be a little bit smarter, a little less searching. So you add that in, you have DPLL. Some people are famous for that. It doesn't seem too earth-shattering now, but that's the 70s for you. So let's conclude it. So propositional logic and other formalisms such as first-order logic can be reduced to CNF and then therefore reduced to a SAT problem, or I'll put 3-SAT. 3-SAT or SAT is NP complete. It's the NP complete problem is the first one to be discovered as NP complete. So complete meaning if you solve it, you can solve every other problem in NP. That means you can express every problem in NP in that whole set. So we believe the world looks like this in the world of computer science. And this little fringe down here is NP complete. Just like my daughter ran out of space. Great. So if you solve any problem here, you can solve anything going sort of backwards. So it was the first problem historically. They realized, oh, look, we can take all these problems and convert it into this CNF thing and then just solve it. And it's like, oh, that's great. So this is the easiest way to prove something is an NP if you can reduce it to SAT. So it's the NP complete problem. And again, solving SAT means solving all NP problems and logic ones too, which are also, So that's satisfiability for you. Hope you enjoyed it.